It really is an amazing privilege to have Avrim give a talk at our workshop today. So Avrim is a professor at the Toyota Technological Institute at Chicago, and he's done a lot of amazing work in too many areas to list, but I'll still try to make them. Still like to count them out. So theoretical machine learning, algorithm game theory, online algorithms, approximation algorithms, and so on and so forth. And today he'll be talking about learning and intersections with fairness. Thank you so much, Avrim, and the floor is yours.
Thank you. Thank you for the nice introduction, and it's a pleasure to be here virtually. I wish I could be there in person. But oh well, next time. So I'm going to talk about a few pieces of work in the area of learning, incentivizing improvement, and fairness in the presence of strategic agents. And this is joint work with Saba Ahmadi, Hedyeh Beyhaghi, and Keziah Naggita. Saba and Hedyeh are postdocs, and Keziah is a student here. Okay, let me get started. Make sure this works. Okay, so so the first thing I want to talk about is work on strategic online classification, and this is coming from a paper, the strategic perceptron that we wrote is in EC21. So good. So the problem we'll be looking at is kind of, in the context of this workshop. So we'll be interested in classifying entities that will aim to modify how they appear in order to be labeled as positive, say for getting a loan, college admission, something like that. And so we will have a mathematical model where agents can modify their feature values at some cost and some very particular notion of utility for these agents. And then we're going to try to analyze algorithms in this model. And the challenge is that as you learn and modify your decision rule, agents are going to change how they respond. This is going to be an online setting. And so this problem is going to be particularly a challenge in an online non-distributional setting. So we are going to have agents coming one at a time who are not coming from some distribution. So we can't, for example, have a training phase where we collect real unmanipulated data by, for instance, accepting everyone at the beginning, solving for a rule, and then modifying it. We're going to always have to be, trying to figure out, what do we get from the behavior, from the thing we saw. So it'll be an informational problem in addition to a computational problem. And it's a lot like online learning of a Stackelberg leader strategy, except it's new agents coming in one at a time. Okay, so all this, falls under the category, different sorts of names for it, but one I like is measure management. And this is a nice book that I like called What Counts and What Gets Counted, that kind of gets at this issue of the difference between the thing you care about, namely what counts, and the way you are measuring it, and what gets counted, and has a variety of, a lot of anecdotes of places where it's something you care about, but of course you're measuring people, and these people will, if their performance is being measured according to these measures, they're going to modify the measurement without actually necessarily modifying in the way you wanted the thing you care about. And this goes under a number of names like Campbell's law, Goodhart's law, and so forth. Okay, anyway, so the topic of the workshop. So here now, let me get to a very specific mathematical model that we are going to be focusing on here. Okay, so the model is as follows. We're going to be interested in binary classification problems. So, say deciding whether someone gets a loan or not. Our data are going to be points in d-dimensional space. So each individual described by d real valued features. And we're imagining the true data is linearly separable. So something like this picture here, say the blues are positives and the greens are negative. And the agents arrive, the data points, one at a time. Our classifier makes a decision, plus or minus on them. And then we are told the correct answer. Did we get it right or not? So this is a classic online learning model. And our goal is to minimize the number of mistakes. So we get a data point, we have to predict positive or negative. We're told the right answer, we're charged $1, say, if we get it wrong. We want to minimize the number of mistakes. The twist here is that our agents are strategic, and we will assume they have the ability to, in particular, to move themselves in space by a limited amount in, say, an L2 or weighted L1 ball. So L1 would correspond to cost to changing individual feature values. L2 is more of a, combined movement cost. And their goal is to be classified as positive. So, for example, this green point here, maybe it can move in this yellow ball. Okay, and we'll imagine that agents have a linear cost to move, and they get benefit 1 from a positive classification, and they're utility maximizers. So what it means, this is sort of the ball they can move at a cost 1. They could move farther, but that would have cost more than 1, so it wouldn't be worth it. We'll assume that agents know the current classification rule that we're using. So it's a completely transparent system. We are trying to give out loans. We completely specify the rule for, what does it mean to have a good enough credit score? And, agents can move to try to get onto the positive side of it if they can. And so in particular, if the classification rule is deterministic, which it will be in all the algorithms we're going to look at, then agents will only manipulate if it actually changes their classification from minus to plus, because otherwise, why put in the effort? So we're assuming there's a kind of linear cost to move. And if they can do so, they will do it in the cheapest way possible. So for example, this green point here would move perpendicular to the red line and stop. That's what they would do, because that's the cheapest way to become classified as positive. All right, does the setting make sense? So that's the setting. Okay. All right, and so this is actually similar to settings that a number of folks have looked at, in particular one of Dong et al., except in our case, our losses are not convex or continuous. And so as a result, we are only going to be able to nicely handle what's called the realizable case, where there's really a true linear separator. And in particular, what's happening, what makes this challenging is that the agents just care about being classified positive. They don't care about their dot product with our classification rule. They just want it to be bigger than whatever the threshold is to make it positive. So, if they can't do it, they won't move at all. And if they can, they'll do it the cheapest way possible. Okay, so that's the setting. All right, let's look at this problem. Okay, so first, just kind of some related work. There's been quite a lot. I'll just mention a few. So work of Hart, Megiddo, Papadimitra, and Wooters considered a distributional case. They actually looked at different sorts of costs that are separable, that in some sense actually make the problem easier, because it's such a powerful strategic setting that there's much, in some sense, all you can do is solve a one-dimensional problem in their case. But it's kind of interesting that strategic behavior could make a problem easier by limiting the sort of reasonable things you can do. The work of Dong et al. Looked at an online regret setting with convex losses and different agent utility functions. And then another nice piece of work I'd like to mention is work of Chen Liu and Padamata, and they consider a less predictable model for agents, a little bit more like adversarial machine learning, and so the associated benchmark is different in their case. Okay. So with that, let me just kind of give an example of a challenge that comes up here. So let's imagine here's a simple world with 3 data points. They are linearly separable. And let's imagine our agents can manipulate in an L2 ball of radius 1/2. And let's see what would happen if we ran a classic online learning algorithm, in particular the perceptron algorithm. So what is that algorithm? How does it work? Well, the way that algorithm works is it starts by predicting negative until it sees its first positive example, and it sets its weight vector to equal that example. So like here, so we're starting with the weight vector 1, 0, and we're going to predict with w of x greater than or equal to 0. That's going to be our classifier. So the purple line is our classifier. And now maybe this negative example comes along, and its real location is negative 0.5, 1, but it's going to manipulate. It sees that, hey, in order to get a loan, it has to move to the right. And so it will do that because it can. And so we will actually see it over here. We won't actually see it where it is. And we will make a mistake because it's a negative example. So what do? We subtract that negative example from our weight vector to get this new weight vector here. 1 comma minus 1. Okay, so we just subtracted that point. Now along comes this positive example. Now this positive example, it would like to be classified positive, but it's too far to move. This is root 2 over 2 distance, and it can only move a half. So it'll just stay where it is. It's not going to move because it can't move that far. So it'll stay where it is. So we will now see a positive at 0, 1, which is the exact same location as the negative we just saw. We will add it to our weight vector and get back to here. And this, if these 2 points repeat over and over, then we're just going to keep back and forth doing this, when really there was a perfectly good solution. This here, for example, is a perfectly good solution because this is a linear separator where the positive can manipulate, that's less than a half, but the negative can't, it's more than a half. So this would actually classify everybody correctly. Notice that the correct solution here may require manipulation. Okay, so it's just like, you know, when you're reading recommendation letters, right? Excellent means great, great means good, and good means not very good. Right, so you just, you know, you understand that. So the correct answer is going to require the manipulation. Okay, so the standard perceptron algorithm didn't work, and you can show the same phenomena will also occur with L1 manipulation as well. Okay, all right. So that's just to kind of show a little bit about what the problems are. So let's see how we can solve this problem. Okay, so we're going to come up with a strategy, manipulation aware, strategy aware algorithm. We'll call it the strategic perceptron. And let's take the case of L2 manipulation. So agents can move within an L2 ball of some radius R. And let's assume that radius R is known to us. If it's not known to us, we can wrap around a binary search, and I'll say a little bit about that, so we don't actually have to know it in advance, but it's just a little easier to assume that we know it in advance. And again, this is a very stylized model, if it wasn't clear already. All the agents are identical in terms of their ability to manipulate. Everyone has the same radius R. It's all an exact L2 ball, ... Okay. So for example, this agent here, that negative example could manipulate anywhere in, say, a ball of radius, you know, a half, something like that. We will assume that there exists a perfect classifier in the event W star at x greater than or equal to 0, in the event there is no manipulation, so something like this, okay? And so one thing that means is if you just shift it by R units, you will get a perfect classifier in the presence of manipulation. So if everybody can move a distance R, if you knew the right answer for agents that did not manipulate, all you have to do is, instead of looking at W star x greater than or equal to 0, you just shift it over by R units, which is this is shifting it over by R units to get the blue line. And now that will be a perfectly fine classifier in the presence of manipulation because we've moved by R. So all the people to the right of the purple line can move to the right of the blue line, and all the folks to the left of the purple line can't move to the right of the blue line, right? So that negative can no longer move there, but the positive example can. Okay, does that make sense? Yeah, so if we knew the right answer, it would be easy to handle this manipulation. We would just shift it over. So if we had access to clean, unmanipulated data, we could just solve there and then just say, okay, you know, great means good, whatever, and just shift it over by however much. Okay? And so our goal is to find a weight vector that's close to this W star so that we can kind of do the same thing. All right, any questions at this point? All right, good. So how are we going to do this? So for those of you familiar with the perceptron algorithm, there's a certain, basically any online learning algorithm, every time it makes a mistake, it has to make progress. In this model, you don't have to learn from your non-mistakes, but you better learn from your mistakes because you're trying to keep your mistakes down. And in particular, the thing the algorithm needs to make progress, so this will be familiar to you if you know the algorithm, and if you're not familiar with the algorithm analysis, don't worry about it. The thing you need is some point. So given a mistake on some x, you want to be able to update using some x tilde, so some x tilde, that could be X itself or not, with two properties. It should have a positive dot product with the true W star, but a 0 or negative dot product with your hypothesis vector W. If you can find such an X tilde, you can update by adding it to your W. That's actually all the algorithm does, and that will be enough to get a good mistake bound. Okay, so that's the thing we need. And so what I want to do now is go through, well, how are we going to get those things? And so to analyze this, there will be 4 cases, of which the first 3 are trivial, and all the work will be in the last case. But let's go through them one at a time. So let's start in the usual way. We will predict negative till we see the first positive example, X. It's positive, so it has a positive dot product with W star. It has a 0 dot product with our weight vector W, because our weight vector was basically the all zeros vector. We add it. So now we initialize with our weight vector being that example X itself. Great. And now we will predict by using that W(x) greater than equals 0, but shifted over by our units. So we will use the blue line as our classifier. So now what do we do if we make a mistake? Using this blue line as or blue hyperplane really as a classifier. Right. The green thing is a vector, the blue thing is the perpendicular hyperplane. Okay. So first of all, easy case number 1. Suppose we make a mistake on a positive example X that is to the left of the purple line. W(x) is less than or equal to 0. Well, then we can update using it directly. This point X did not manipulate. There would be no reason to manipulate and still be classified negative. So that point really has a positive dot product with W star. It is a true positive example. So it satisfies this first condition. And it's to the left of the purple line, purple hyperplane. So it satisfies this condition. So we can update using it directly. Great. Now, what about making a mistake on the positive point that's to the right of the purple hyperplane, like here? That would satisfy this first condition, but not the second one, because it actually has a positive dot product with our current vector W. So this would be a problem. Luckily, this should never happen. Why? Well, because if this was the true unmanipulated location, he would have moved to here, because it's distance less than r. And if it wasn't the true location, what's it doing manipulating to some point where it's still being classified negative? That makes no sense. It's not a rational thing to do. So the point there should never be any example there. In fact, if you see an example there, what that means is that if you thought people could move this far, they really can't, because he would have moved if he could. So that means your guess for r is too big, and you can use this in the binary search in the case that you don't actually know in advance how far people can manipulate. Okay, good. So this case would be problematic, but luckily it should never happen. So we don't have to worry about it. Okay. Third case, also an easy case, is a negative example that is strictly to the right of the blue line, the blue hyperplane. If you're strictly to the right, then that means that that point did not manipulate, because why would you move farther than you had to? So that means it's a true negative. If it's a true negative, it means you can flip it through the origin to make it that a true positive, an X tilde, that will indeed be a true positive, and it's to the left of the purple hyperplane, so it satisfies this condition, so great. So there's only one case left to go, which is a negative example that's exactly on our blue hyperplane. It might have manipulated, we're not sure. So what will we do? Well, we know it moved the direction it moved, which is perpendicular to the blue hyperplane. So we can, and it moved at most a distance r. Let's pull it all the way back by distance r. It maybe didn't, it may have come from in the middle, but let's just pull it all the way back, flip that through the origin, and update using that. So that point X tilde satisfies this by design. It's on the blue hyperplane, so its dot product with W is 0. But why does it satisfy this condition here? Well, the reason is because of a property that I haven't said yet, which is that by induction, the algorithm maintains the property that the current weight vector W always has a positive or at least non-negative dot product with the true vector W star. And what that means is that even if we subtract a little bit too much here, we're subtracting a little bit more times W. So what's going on? It originally came from somewhere here. We pulled it back a little bit too far. But by subtracting a little bit more of W, that only made it more negative than where it really was. It was really here and was negative for W star. You pull it back, you subtract a little W, it only becomes more negative for W star. So when you flip it through the origin, it's only more positive, and so it still satisfies this condition that we want. Okay, so that's how this analysis works. Okay, and so yeah, so this gives you a bound that this algorithm makes actually not too much more mistakes than the standard perceptron makes on the standard non-strategic case. Okay, so that's a nice statement. And then we can extend this to known weighted L1 costs. The difference in the L1 setting is that in L2, agents will move perpendicular to your separator. In L1, they will move along a coordinate axis, whichever one is giving you the most bang for the buck. So as you modify the separator, they might move on the X1, they might move in X2, whichever way gives you the most bang for the buck. That's the way L1 movements work. And if you know the costs, so you know that, say, moving horizontally is twice as expensive as moving vertically, you can use that in your current weight vector to determine the direction they came from, not necessarily how far, but at least the direction. And that's good enough, and we can do the same analysis we've done so far. Okay. For unknown costs, we're currently exponential in a number of unknowns. So, okay, so that's the end of the first part of my talk. I just want to mention, before going to the next part, two nice open problems. So here's a problem which, I think is interesting and kind of, I think it's a nice question, is can you extend this to a bound in terms of the hinge loss of the, okay, step back. I made the assumption that the original non-manipulated data was perfectly separable. In the non-strategic case, the perceptron algorithm and things like SVM, they all can give you a bound in terms of the hinge loss of the data. It's not how many mistakes the best separator makes, but rather it's more like how far you'd have to move the points to put them on the correct side by a nice margin. Okay, that's the hinge loss. And can you extend that to the strategic case? So can you get a bound in terms of the hinge loss of the original unmanipulated data? Now, just to be clear here, that one thing it's trivial to do is to get a bound in terms of the hinge loss of the observed data. So if you look at the data you see and say, gosh, what would be the separator of smallest hinge loss for the data you saw? Yes, you can get a mistake bound in terms of that. In fact, that follows from the standard perceptron algorithm analysis, because the standard perceptron algorithm doesn't care how the points got created. It just gives you a bound in terms of the points you see. But it's not so meaningful, because it could be that the reason there is no good separator of low hinge loss is because your algorithm was bad, jumping around all the time, causing people to move around all sorts of different ways, and therefore there's not a good separator. But had you behaved differently, there would have been a separator with low hinge loss. The algorithm I gave handles that in the case that, yeah, had you behaved differently, there would have been an algorithm with zero hinge loss. But if it's not zero, that analysis breaks down. And if you want to know where it breaks down, it can be fooled by even a single bad example at the very beginning. And that single bad example will break this inductive assumption that you have a non-negative dot product with W star. And once you break that, it can, a bad sequence can continue to have you pointed in the wrong direction. You think you're making progress, but you're really not. Of course, you can fix that problem by restarting the algorithm, but that doesn't really fix it, just in that particular example, because then what if you get another bad one? In any case, we do not know a bound in terms of the hinge loss of the original data. I think that would be really interesting. Another nice question is, can you get meaningful bounds for the kernelized setting? One nice thing with SVMs, perceptron, and all that is that you can kernelize them. However, kernelization breaks the idea that people are moving an L2 ball, because that's not an L2 ball in the kernel space anymore. And so kind of all hell breaks loose, and we don't know how to make things work. Anyway, okay, good. So now let me move on to the next. I'm going to talk about two more things briefly. Okay. Good. So the next topic I want to talk about is combining gaming and improvement. This is also, all of this is work joined with Saba, Hedyeh, and Keziah. Okay, so good. So we've assumed that agents are, just manipulating. They're just gaming. They're not actually changing their true locations. But you can imagine that some directions correspond to kind of manipulation or gaming, but others are true improvement. For instance, maybe you have a loan criteria that puts some weight on having taken a money management class. It's an action you can take that will actually improve perhaps your ability, or the chance that you will pay back that loan. Okay, so that could actually improve you and make you loan worthy. Okay, and in general, there's been a lot of recent interest. I just listed some papers here in models that combine gaming with true improvement. A lot of really nice work. In our setting, we are going to consider a goal. So think of a bank giving out loans, of maximizing true positives. So positives that you correctly classify as positives. These are loans given out to qualified applicants, subject to few false positives. So loans given out to unqualified applicants. Okay, so that's the kind of goal we're going to think of, right? Something you might imagine the bank wants to do. They want to give out loans to qualified applicants because they want to, that's how they make money, but they don't want to give out loans to unqualified applicants. And what's interesting about this goal, if you think about it, is even a perfect classifier might be suboptimal if it doesn't incentivize people. So imagine, for example, that nobody is qualified for a loan. Okay, you can correctly classify everybody, but you won't be giving out any loans. You'd be better off if there's some way that you can incentivize people to become loan worthy by taking that money management class so that you can actually give them out a loan, because that's how the bank makes money. Okay, so it's kind of an interesting setting, because being a perfect classifier is not, maybe you might still be leaving, positives on the table, potential positives on the table. And so we'll look at this problem in the batch setting. And we actually look at two versions of this, and I'll kind of briefly mention each. The first version is a linear model where we think of, again, points in RD. The true decision boundary is a linear separator. We'll think of some directions as being gaming directions and some as improvement directions. We'll imagine L1 costs to increase coordinate values, so decreasing is free. So, if we're going to measure some quantity, it's easy. For free, you can look worse than you really are. Okay. The algorithm's classifier may or may not be a linear separator. Okay, so we can allow just we'll imagine that there is a true linear separator, but the algorithm's classifier could be whatever it wants. And so let me just show an example of something that, kind of interesting can happen here. So let me unpack this picture. So this is a two-dimensional picture. Improvement is to the right and gaming is up, and maybe improving costs twice as much as gaming. In this example, there are 3 data points circled here in purple, x1, x2, x3, and this is where they live. And then F star is the true correct classifier. And that classifier is correctly classifying x1 and x2 as negative and x3 as positive. Now, in the presence of manipulation, this wouldn't do great because x1 and x2, let's imagine that the manipulation budget is fairly large. They could move straight up if they wanted to, because gaming is, in this example, twice as cheap as improvement. So they would move up rather than to the right, and they would game and be classified positive if they really aren't. Now, of course, you could fix that by just shifting the separator parallel to itself as far as needed, so that these, x1, x2 can no longer game, but x3 can. And so, however far it takes to based on the costs, you could do that, and that would correctly classify everybody. It would correctly classify x3 as positive and correctly classify x1, x2 as negative. But that's maybe leaving money on the table. Instead, if you were to use this non-linear shaped region shaded here in kind of gray, let's see what happens. Now, if we look at x2 over here, it has a choice to move to the right or move up, but it's twice as far to move up as to the right. So it would rationally decide to move to the right and actually become positive, because that's true improvement. x1 over here will do a combination. It'll move to the right and up. And I've written here kind of, it starts off at x1 and it moved to the right, and then the moving up part is just gaming. So our classifier sees this. That's the perk is for its perceived location, but really it's sitting here because the upward movement was just gaming. But nonetheless, that's a true positive. And so it actually improved itself enough to become positive. And the x3 would just improve itself to become here. So this classifier would actually allow you to give out 3 good loans. So it would correctly classify everyone and classify them as positive, which is better than just correctly classifying them the way they were originally. Does the example make sense? Okay, good. So yeah, so that's then kind of the problem is how can we do this? So so a couple results. I think there's a lot open here that we don't know, but just a few things that we were able to figure out. One is that in 2 dimensions, you can indeed efficiently solve for a solution that maximizes true positives subject to no false positives, like this picture here. But in general, D, this is NP hard. In fact, it's even NP hard in general, D, to determine if you can incentivize everyone to become positive. On the other hand, you can efficiently find a linear classifier that incentivizes everyone to become positive if such a linear classifier exists in general D. That you can do with linear programming. Okay, so those are just a few statements. And then I would mention another model we looked at, which is in some sense more general, but in some sense less. We call it general discrete model. And here we imagine that space is discretized into n pieces, like in this picture here. And the classifier can label any subset of them positive and the rest negative. So here we've labeled 5 of them blue positive and 4 of them red as negative. And then for any given agent, and then the true classifier could be, the true function could be anything at all. And now for any given agent I in any given piece J, moving to piece J has some cost, Cij, and may or may not make the agent truly positive. So in this general model where we imagine the true classifier can really be anything, and what our algorithm can do is just label some subset of these n pieces as positive, we can view this as the following bipartite graph problem. We have n agents over here on the left, little n agents, capital N pieces over here on the right. And for every agent on the left, it has some cost to moving to each piece. So Cij to move for agent I to move to piece J. And that movement might involve some combination of gaming and improvement that may or may not make the agent truly qualified for the loan. So let's color the edge blue if it actually makes the agent qualified, and color the edge red if it doesn't. So we have a bipartite weighted graph with the edges having 2 colors, blue and red, where blue corresponds to yes, this made the agent qualified, red corresponds to no, it didn't make the agent qualified. So like in this particular example, maybe agent 2 was already qualified, and so it doesn't matter if they'll stay qualified no matter what they do. But agents 1 and 3 initially were not qualified, and they might or might not become qualified for the loan depending on which piece they move to. Okay? All right, so that's the setting. And then our goal is to pick a subset of nodes on the right-hand side so that what? So if each agent on the left moves to its cheapest neighbor in the subset we picked, so it does the cheapest, the cheapest way it can get qualified for a loan, or it moves to none of them if they're all too expensive. Maybe all the options are beyond its budget, so it just does nothing. If that happens, what we would like is many blue edges to show up and not too many red edges. So the blue edges all correspond to people that we give out loans to who are qualified, and the red edges taken are people we gave out loans to who are not qualified at the end. Okay, so that's what we want. So this is our general, kind of very general model, but it kind of requires discretization. And so one thing nice here is, yeah, maximizing blue subject to no red, that can be solved efficiently. And what's interesting about this solution is it's actually pointwise optimal, meaning that if someone doesn't get a loan, you can say, well, sorry you didn't get the loan, but actually there was no way for me to give you a loan without also giving out a loan to somebody who wasn't qualified. Okay, and also of min cost. So min total amount of effort done by the agent. On the other hand, maximizing blue subject to most k red edges taken is NP. Okay, so those a few things you can say. All right, and another nice thing another thing you can ask here is, what about learning from data? So I assumed here that we had upfront all the agents, all their edges, all the costs, and we were going to algorithmically, you take in as input, all the things about the people, and you have this whole graph in front of you, and you're trying to figure out what to do. But what if you don't have the graph in front of you? Well, let's imagine there is a probability distribution D over agents. So what does that mean? It's some probability distribution over nodes on the left. What's a node on the left? It's really kind of a vector of costs and colors, right? Like it's a distribution over, so what's an agent? An agent is something that has costs to go to each piece on the right and colors for each of them. So it's kind of just a vector of cost color pairs over the n pieces. So but there's some probability distribution over them. And we can imagine a full information model where we see all their out edges. So that's kind of like we get a focus group. We pay, 20 people to come into our laboratory and we ask them lots of questions and we figure out, this graph. Or we can imagine a natural partial information model, which is, all you can do is pick some subset of the right-hand side. This is more like online learning. You pick some, and you're going to pick, you say, okay, you're qualified for the loan if you satisfy condition 1 or condition 3, but not 2 and 4. Okay, so you pick the subset 1, 3, and then an agent comes along and you see where they go. They satisfied condition 1, and if their edge was blue or red, you gave them a loan and did they pay you back? So you see, it's just like the online mistake-bound model, except we're assuming they come from a distribution. Okay, so all you can do, the only access you have is you pick some nodes on the right, some agent comes along, they take an edge, you see where they landed and whether they actually became truly qualified or not. And then the goal is to find a subset of nodes on the right-hand side that gets you a large probability mass of true positives, say within some epsilon of some optimal, and at most epsilon probability mass of false positives, where our notion of optimal, the thing we're comparing to, is the best you can hope to do subject to 0 false positives. So this is a bi-criteria thing. We are going to find a solution that is nearly as good in terms of true positives with at most epsilon false positive rate with respect to the optimum that has a 0 false positive rate. Okay, and it turns out you can achieve that in both the full and partial information models. Okay, and basically it is an online learning algorithm. All right, good. So let me now just turn to the last topic I want to mention, is about fairness in helping agents improve. So so far we were talking about the improvement. We didn't actually, we cared about giving out loans. We weren't really trying to sort of improve agents' quality other than making them, qualified to give out the loans that we have to give out. Okay, but now we're going to be looking at the problem of fairness and helping agents improve. So this is going to be much simpler in some ways. We'll be looking at just a one-dimensional problem here. So let's consider the following one-dimensional problem. We have a collection of agents, and they each have a single real valued skill level. So these are maybe employees at some company, and they have some skill level, and it's just one-dimensional, or it's students with some just think of it like an SAT score kind of thing. Just that we imagine we've compiled everything down to a single number, which of course is unrealistic, but hey, start with 1, right? So we have a single one-dimensional skill level. And what we can do, so the kind of action we can take is we can select K targets and think of these as like projects or trainings. These will be points on the line, like here, 3 targets. So think these are like projects or trainings that if you do it, it will improve your skill. Okay, you can think of them as tests. So we're going to pay you $100 for passing a test. And let's imagine that every agent they will choose the closest target greater than where they are if it's within some distance delta, otherwise they do nothing. So in this case, if there is a project or training or a test that is, it has to be challenging, has to be above their current skill level, but not too much above. If it's more than delta, they can't do it. So this person here, unfortunately, has no test they can take that's above their level, but within delta, this person has nothing they can take that's above, but everybody else is able to improve to the value of that test, that project or training. So the total improvement is the sum of the lengths of all the blue arrows. That's how much improvement happened here. Okay, so we were able to put down some targets. These are challenges or tests or targets or projects, and agents will we'll assume that each agent will pick the easiest one to do that's above their level, and will do that and improve up to that level. So that's the model, and our goal is to maximize total improvement and to do it in a fair way once we introduce fairness. Okay, so that's the problem. This is very closely related to a paper on algorithms and learning for fair portfolio design, where you're trying to put portfolios slightly below where people are. But there's an interesting non-monotonicity in our setting here that makes the problem different and also makes the fairness issue a little tricky. Okay, so what do we mean by fairness here? There's multiple things one could mean, and I'm just going to pick two things that one could mean. So first of all, let's imagine there are multiple groups. So for instance, there's the green group and the purple group. We can see here the purple group is being helped a lot more than the green group because there's only one green agent and they're moving about this much, and whereas all the purple agents are improving a good amount. So we have two of the green agents aren't being helped at all. So we would like to help each group fairly. So what could that mean? So there's a few things we might mean. One easy notion is min-max fairness. So maximize the minimum over the groups of the total improvement in group G. So this solution here, the minimum group would be the green group, and they're helped by a single blue arrow of this length. So that's how much improvement they get. The purple group gets more. And so from that perspective, you'd want to move these guys around to help the green group more. Now, one issue with min-max fairness or max-min fairness is it could be that there is some group that's just very hard to help. They're all spread out, whereas another group is pretty concentrated. And so this would sort of force you to use almost all your resources on the one group that's hard to help and end up not helping the other group very much at all. So another notion we look at, and I think it's kind of more interesting in this context, is the following. Can we give the following guarantee? That for each group, we will help that group by within a constant factor of the most we could possibly help that group if that group was the only group we cared about. Okay, so we'll tell the green folks, we will give you within a constant factor of the most that you could get if you were the only people that matter. And we'll tell the purple group the same thing. Okay, so can you give, within a constant factor of what you could hope to do if you used all your resources on that group? And the answer is yes, as long as there's a constant number of groups. And one of the, and I'll get to that in a second, but a challenge here that's want to mention is there is a kind of trivial way to try to solve this problem. If there's two groups and, our big O is say, we're willing to be within a factor of 2 or 4 or something, say 2, you could say, all right, I'll just use half my resources on the green group and half my resources on the purple group. So if I've got 4 targets, I'll use 2 of them for purple and 2 for green, and I'll help each group within a factor of 2. I should mention this is some submodular or convex. Adding the extra benefit of another target that keeps dropping, right? So it's so you could do that. You could say, let me just use half my resources for one, half for the other. And that would be fine, except for one problem, which is that there is a non-monotonicity here, which is adding a target can actually reduce improvement. So if, for instance, I were to add this green target here with the goal of helping that green agent, then all of a sudden that purple one over here is going to improve less because they now have a simpler, less challenging test. If we kind of, if we simplify the test to help some people, that might hurt others because now they're not challenged so much, and so they don't improve as much as they would otherwise. So actually, in this context, you can't, if you find the optimal solution for one group, the optimal solution for another, and then overlay them, that could actually be a really horrible solution for one or both of the groups. So you can't just do that. Okay. But so the main technical result we have here, though, is that if the number of targets is at least the number of groups, there always exists a solution. This is a structural statement. There always exists a solution that has the property that it gives each group within a 1 over polynomial in the number of groups fraction of the maximum possible improvement you could hope to give that group. And then once you have that structural statement, now you can just go ahead do dynamic programming to find the Pareto curve of solutions and extract out the solution that has the property you want. Okay, so actually this is a problem where finding is not the problem. That they just do dynamic programming, get the whole Pareto curve. The problem is showing that there exists a solution that actually has those properties. Okay, and then you can get generalization guarantees for this. This is on the assumption you have the agents. What if you don't? What if you have a sample? Using techniques of Balka and Dick and others, you can get generalization guarantees for this. Okay, so that's those are the things I want to talk about. So just kind of summarize. I looked at I talked about 3 problems. One is strategic classification with the perceptron algorithm, and I introduced the strategic perceptron algorithm here. It achieves nearly the same guarantees in the strategic setting as the standard perceptron algorithm does in the non-strategic case, at least for the realizable, for data that's actually linearly separable. We also looked at the case that agents can both game and improve, and in that case, our strongest results are in this general discrete model and 2-dimensional linear model. And we also looked at a 1-dimensional model where the goal is to help agents improve, and we consider a fairness goal of helping each group within a constant factor of the most we could possibly help if we'd allocate all our resources to that group. And the tricky issue here is that's non-monotonicity. And then just to mention 2 nice open problems. One is, can you get good bounds in the strategic perceptron case in terms of the hinge loss of the unmanipulated data? And we have a counterexample to the algorithm we have, and we don't know a good algorithm for that. And can you get good bounds in the kernelized set? And that's it.
Thank you, Avrim. Questions from the audience?
Thanks for the talk. I was wondering if you can help me understand a little bit more, like what your long-term vision for this research project is, and in particular, are we hoping to create algorithms that are deployed, or are we hoping to gain kind of conceptual insights, and what types of algorithms or insights would be, or something else, be kind of hoping to develop here?
Okay, yeah, that's a great question. I mean, as a theoretician, my interest mainly is that what is to try to see if we can get insights into the idea of classifying, applying machine learning to entities that will respond, right? I mean, that's sort of a in particular, it's interesting in the online case where in an offline case where you could say, well, let me just get some real clean data, maybe solve and then just move my solution. I think the online case is interesting because you never quite get real data. So so how do we do that? So I think that's just a question of what's doable. Like, can you is this, do kernels work with strategic agents or not? I mean, it just seems like a very puzzling question. Or, in fact, even the simplest thing, like the very simplest trick in a normal perceptron is using non-zero thresholds, right? If you want to have a linear separator, it doesn't go through the origin, it's trivial. You add an extra feature, you set it to 1 and everything. Now you have one more coordinate, you go through 0 in the new space, which is going through a non-zero in the original space. That reduction doesn't work here because they can't manipulate in the new ones. They're not moving in a L2 ball anymore. And so you can still solve that problem, but it's more painful. So it's kind of, well, what are the tools out there? The reductions, the standard reductions are failing. Are there other reductions here? So I think there's just a lot of interesting, it's kind of like it's kind of an analog of saying, gosh, looking at another complexity measure almost. We have strategic agents. How does that, all the algorithmic tools that we have, how does this affect them? So that's one interest, I think. Another one, and it may be more social level. One thing I think is nice is the notion of transparency. So although this strategic model is very stylized, everyone can move and there's balls, one thing it relies on is the assumption that the agents, everything is public. the agents know the classifier you're using. And that's kind of nice, because my hope would be that if you can actually deploy algorithms that are strategy aware, that will then incentivize the deployers, the loan givers and so forth, to actually make their rules public. I mean, because one reason you might want to keep things private is that you're worried people might, manipulate to them. But if you have something that's strategy aware, then, then there's, in fact, you're relying on people manipulating. So you want to make them transparent and public. So maybe this is some way of improving transparency by having a model where really to do well as the decision maker. God, I almost said decider. As a decision maker, for the younger folks won't get that. Then you want to get transparency, in the system.
Hi, you might have just answered my question, actually, but I was thinking back to, I think, the first and the second stories. And I think you were assuming that the agents were fully strategic and rational, and that they had knowledge of the decision boundary.
That's right.
Right. So my kids are applying to college now, and I'm working very hard to manipulate them. And I do not have knowledge of the decision boundary, unfortunately. So I was thinking about that while you were giving that presentation, but maybe what you just said is part of the answer to that question.
Well, so I think your point is a great one, that this is very stylized in I guess, two respects. One is knowing the boundary, and two is knowing where you are, right? So like, you don't know what features are being used. You don't know where you are in it either, right? So although it's interesting, actually, I remember when my kids were applying, that at some of the state schools, at least, it was actually, you just need to get this score on this test, right? So there's a kind of nice feature about that, about knowing whether you made it or not, in advance. But you're right, you don't know. And, and what does it even mean? Like, the essay that you're writing, like how do you don't know how that's being viewed and how it's being scored. So you see, you're right, kind of a more, this is very stylized, and in some sense, actually, models where people don't know are maybe almost easier to deal with, because now people will just manipulate as much as they can, maybe, okay. Anyway, you're right, this is not realistic in that sense. Absolutely, I completely agree with you. But the hope would be maybe we can hope to, if we get some good algorithms to incentivize decision makers to be more transparent, which I think in general would be good, although you could argue sometimes it's not great, but I think in general it's good. So I don't think I have anything smart to say other.
I had one other question. Regarding the non-monotonicity, and this may have been something that you addressed and I just missed the fine details of, but when you were talking about the result where it's like you can add a target and actually reduce the overall total improvement, how much of that is based on the idea that someone always moves to the closest target within their ball? In other words, if there were two targets within my little delta ball, and I could and say we added, or there was only one within my delta ball and you added one closer to me, but I could still in principle go to the further target, which would say improve my skill level, which is a continuous value more. If we instead assumed that agents go to the furthest skill level within their ability to manipulate, do we then get monotonicity back?
Yeah, yes. So then you would get monotonicity back. So, right. So this does very much that problem, definitely, it comes from if we're going to think about this as, I don't know, students are at different levels and this is going to be what they need to graduate or something like that, and that people are going to do the simplest thing they can, right? Then it really is relying on that, but right, if you could, for example, if I give you $100 for taking, whichever test is Like I know where your location is, and you're only allowed to take tests above where you are. But yeah, he's right. It's a very particular model. So if you had a different model, then that could fix that problem. Yeah, I guess we were initially thinking about this in a context of, I don't know, maybe like employees of the company, and then you want to set like promotion levels or something, and then, you know, and people can maybe only be promoted one level. So between here and here is associate, here and here is senior associate, here and here is junior, whatever. And so people would go up to the closest one. But yeah, I mean, definitely that, if you change that assumption, that would indeed address that problem. So you're right. Completely. Mm-hmm.
So again, on the subject of uncertainty, so Braverman and Garg have this paper where they argue that having randomized classifiers can allow for better strategic learning algorithms. Have you thought about whether you can gain anything in the perceptron setting with as opposed to a hard boundary between 0 and 1 probability of being classified, having some smooth?
No, that's a great question, and that's right. So by there's a few things actually randomization can do. So like in the Braverman Garg paper, you can, if you have enough randomization, then maybe people won't strategize at all, because the cost to move is basically if the probability of being classified positive, if that's Lipschitz and kind of at a lower rate than the effort, then it's why do the work, right? So if the probability of getting accepted is going up by less than the amount of effort, then you won't do it. So that's one way, but it actually can help in multiple ways. So in some sense, one of the big challenges is you can't invert the manipulation function directly in our model. You see where they are, you don't know where they came from. It's possible that with randomization, you could do that inversion, because, you know, if they had started here, they would have moved a little farther. Here, they would have moved a little less. Then you can go ahead and invert that and then use that for learning. So it does seem possible that might help. You know, we weren't able to figure out something, but definitely randomization could really help. Yep.
Hi, Avrim. Thank you very much for the very interesting talk. I would like, actually, one of the questions was connected with the previous one. For example, for the classical perceptron, we have a smooth analysis framework. What a smooth analysis framework should say about the strategic perceptron? This is my first question. And my second question is a little bit more open-ended. I mean, from optimization framework, can we see somehow a black box where we could add in, let's say that we want to minimize a classification error, can we see somehow a regularizer that could be added, or a transformation in the optimization problem in order to make it fair somehow, to introduce the fairness as a restriction? This is a second, more open-ended question. Thank you.
Let's see. So with the first question, so about smooth analysis. So right, in the standard case, basically, right, what smooth analysis lets you do is kind of assume a margin, even if maybe the worst case data maybe doesn't have much margin, but with random perturbations, it's very unlikely that it would simultaneously be linearly separable, but by only, say, an exponentially small margin. Right. So, and so that's still true here. It doesn't seem, though, that the smooth analysis helps, you know, helps a lot with the strategic issue, just because, like, the bad cases for the standard perceptron, if you'd move the points a little bit, the algorithm would kind of behave the same way. It wouldn't kind of fix it. So, okay, at least I can say that for the standard non-strategic perceptron, a smooth analysis model won't all of a sudden make it work in the strategic case. Yeah, the bad examples we have for the strategic perceptron algorithm in the case of hinge loss, I don't think they are very sensitive to the exact precise locations. So yeah, I mean, I guess I would say it's you know, always good to keep in mind, you know, right? But I don't see it addressing. I could see randomization being a solution to some of these. I just don't. At least the problems don't seem to be ones that smooth analysis would fix. But you know, until you know a solution, you don't know, right? So yeah. And the second question, so regularizers for fairness. Yeah, I mean, actually, it's interesting because one thing, it's normally regularizers are things kind of you do on. Well, I guess that you apply them to. I mean, maybe there are, you know, basically what you're trying to do is weight yourselves towards certain kind of solutions and keep yourself away from other solutions in a smooth way. And yeah, maybe. Okay, it's a vague question, so I'll give a vague answer. Maybe. How about that? So I don't really have much to say.
Okay, great. Yes. Okay, hi everyone. Great talk. Thank you again. I have a question actually, and maybe it's a question about the framework. So in this kind of framework, it's a necessary component is that I announce somehow like my decision algorithm, right? This allows for the participants to strategize. But it seems to me that like such a commitment would introduce almost invariably a new strategy component, like competition between different service providers. So if I'm a bank and you say, oh, I guarantee loans for everybody that has at least this set of characteristics, and I'm Bank of America. I mean, the next day I'm Citibank and I'm saying like, oh, you know, I'm going to give you a better deal. So by the way, Bank of America, I won't see a single client because my new advertising campaign is that whatever they offer, I'm offering a better deal, right? And then won't that lead to a kind of like bidding war? And then how does that affect this calculation?
Yeah, I don't know. So I mean, you're thinking now it's a game among the agents. I guess there's two aspects of that. Then maybe partly it gets back to randomization, which is, you know, it may be that if you have to announce something, maybe that thing should be a probability distribution. That's one way of, just in general in games, you know. I mean, I guess, okay, yeah, I don't know. I mean, normally when we have games, we kind of do sort of imagine that each player knows what each other's doing. That's sort of the equilibrium notion in a game. But on the other hand, we do typically think of, you know, mixed strategy equilibria. So yeah, I don't really know. And I kind of wonder whether people would like this randomization. Okay, actually, this brings up another issue. So while randomization may address some of these things, like I'm not sure that people would view a randomized rule as transparent. Like, would you like it if kind of, okay, in order to get an A in the class, you need to either, you know, with 90%, I'm going to flip a coin, see, and you know, based on how the coin comes out, you might get an A or a B, depending on. I'm not sure people would be too excited about that. But on the other hand, you know, maybe it just depends on the context, right? Yeah, I'm not. So maybe randomized solutions really, you know. Okay, so I guess why am I getting to that? Yeah, so you're definitely right. You're bringing up an issue of the game theoretic aspect, and yeah, I don't really have anything to say there. And if randomization is actually an answer to some of these problems here, even if it's just the decision maker versus the entities being decided on, it's going to be even more of an issue, I think, when there are multiple agents making out the loans. That's all.
Yes, I think we have one last question. Thank you.
Sorry, this is just a quick question about a possible selection issue, and I may be misunderstanding, but in the like simple strategic perceptron case, when I'm a bank giving out loans, I only observe whether you paid back the loan if I gave it to you. And similarly, I only observe whether you would not have paid back the loan if I give it to you. Now, because perceptron only learns from its mistakes, there's only a problem if like you would have been positive, but you were negative. I'm just wondering whether the strategic perceptron would work in that setting where I kind of miss all of the positives that I misclassify as negatives, which I think is accurate to like the loan setting.
Okay, that's a great question. So basically, we've been operating in what's the classic mistake-bound model case, where after you make your classification decision, you are told the right answer. And what you're talking about is what's sometimes called the apple tasting setting, where if you don't taste the apple, you don't find out if it was good or not, right? You don't give out the loan, you don't know if you made that mistake or not. Right. And that's a great question, and we did not consider that model. And yeah, that's a really nice question, because a lot of results for standard online learning do translate over to this apple tasting model, and the regret bounds and all those things, where, you know, basically the algorithm is, what you do is you take your standard algorithm, but instead of classifying negative, well, with some small probability, you taste the apple anyway. So classifying negative, you convert to, well, 90% chance negative, 10%, I'll give them out the loan anyway, just to get that information. And that 10% will drop to 0 over time. It'll be like a 1/√t kind of thing. And that's the sort of thing you'll do to get those statistics. Maybe, I don't know, maybe √t or t to some power. Anyway, you'll drop at some rate to get that statistical information. And I don't know if that would apply here. That's a really good question. I don't know the answer.
Thank you.
Great. Let's thank Avrim again for the great talk.